Okay, so now we have our cast of characters, and I want to remind you again what the cast of characters that are going to play in the Polya enumeration theorem are in the particular case of our six-beaded necklace. So we have the beads, which we're calling nodes. We have a set of symmetries, which we're calling G. And then for each symmetry, we have this this cycle number. And so I've gone ahead and calculated this cycle number in each of these cases. So we calculated the first four in the last video, and I suggested at the end of the last video you should calculate these. This is what I get. Tell me in the comments if you get something else. All right. So now we have all of this. We're ready to see the actual statement of the Polya enumeration theorem. And here it is. This is the Polya enumeration theorem. So what this says is that if you're in this setup where you've got some nodes on your structure, you want to color them, we've named the number of colors M. And so we're asking how many ways can I color each node with one of the M colors? And I want to account for this symmetry. And so the answer is given by this formula, where I sum over the symmetries of the number of colors to the power of the cycle number of that symmetry, and then I divide by the number of symmetries. Okay. So if you want, although maybe this isn't super intuitively meaningful, this is really saying you take the average over the group members, or over the symmetry group members of the number of colors to the power of the number of cycles. Okay, so I want to apply this formula in the specific instance of our group here. So this is our six-beaded necklace case. And so if we want to do the problem where we're saying that we want to color it in black and white, then that is to say M is 2 in our case. Okay. And so then the number of colorings should be equal to 1 over the number of symmetries, which is 1/6, times, and then 2 to each of these powers added together. So that is 2 to the 6th plus 2 to the 1st plus 2 squared plus 2 cubed plus 2 squared plus 2 to the 1st. Okay. And then we'll go ahead and we'll take this sum, and if you like, we will get 1/6 of 90, which is 15. Okay, so this is the right answer to the number of ways to color our six-bead necklace in 2 colors. It's 15. Okay. As a helpful exercise for yourself, I recommend 15 small enough, write them all down and convince yourself that 15 is really the right number. Okay. What I want to see next, before we sort of wrap up talking about beaded necklaces and talk about applying this very general theorem in other cases, I want to see what happens if we instead look back at the 5-bead necklace case. Because remember, we did the 5-bead necklace case before, but I want to see how that fits into the framework of the Polya enumeration theorem. So I'm going to draw my 5-bead necklace here. So there's bead 1, bead 2, bead 3, bead 4, bead 5, hopping around like that. So that's our node set. 1, 2, 3, 4, 5. Okay. We pretty much know what our symmetries are going to be. Do nothing. Rotate once. Rotate twice. Rotate 3 times. And rotate 4 times. And you can't rotate 5 times now, because if you rotate 5 times, that's the same thing as doing nothing. Okay. So what do we want to count now? we need to count what these cycle numbers are. Okay, so the cycle number of the identity, what's that going to be? Well, that's definitely going to be 5, right? Because under the identity, nothing moves. And so where can 1 get? Nowhere other than 1. So the cycle number here is 5. Okay. Now I want to count these other cycle numbers. Okay, so what is the cycle number of R? So again, let's look at what happens if I start at 1, then I go to 2, then to 3, then to 4, then to 5, then back to 1. Okay. Which is to say that all of these things, they're all in one orbit. And so this cycle number, it's just 1. Okay, let's do the cycle number of R squared. Okay, and I'll do this one out, because this one will have to follow a little bit more carefully. So I'm going to start at 1 and say, where do I go from 1? From 1, I go to 3. Where do I go from 3? From 3, I go to 5. Where do I go from 5? From 5, I go to 2. From 2, I go to 4. And then from 4, I go back to 1. Which is to say that if you follow this symmetry, that is the symmetry where we rotate twice, you actually go from 1 to everywhere. You just go from 1 to everywhere in a bizarre order. Instead of going 1, 2, 3, 4, 5, you go 1, 3, 5, 2, 4, 1. Okay. So this, C of R squared, the cycle number, it's also 1. Okay. What if I were to take C of R cubed? Okay. Well, I'll do that. We'll do it in blue pen and see how terribly this goes. Okay, so I rotate now from 1, and I rotate 3 times. 1, 2, 3. So I go from 1 to 4. Okay, I rotate now 3 times from 4. That will bring me to 2. I rotate from 2 3 times. 1, 2, 3. That will bring me to 5. From 5, 1, 2, 3. Sorry, from 5, 1, 2, 3. And from 3, 1, 2, 3. Okay. And what you'll notice is we traced exactly the same 5-pointed star. With CR cubed, we only traced it backwards instead of forwards. So before, when we did R squared, we went from 1 to 3 and then followed it forward this way. When we did R cubed, we just did that backwards. Okay. And the reason for that actually isn't too hard to understand. What really happened here is that R cubed and R squared, they're inverses. They undo each other. So R cubed is just R squared backwards, if you want. Okay, so this is 1. Okay. So only one more of these left, C of R to the 4th. Okay. And R to the 4th, you can convince yourself, that's R backwards. In particular, going forward 4, 1, 2, 3, 4, that's the same as going backwards 1. So if I think about applying R to the 4th over and over again, that goes from 1 to 5 to 4 to 3 to 2 back to 1. So all of these things are linked. And so this cycle number, it's also 1. Okay. And so what does that mean? That means that if we go ahead and use the Polya enumeration theorem, remember that what we're supposed to do, we're supposed to take 1 over the number of symmetries, and then sum the number of colors to the cycle number of each symmetry. This will be, so the number of colorings is going to be 1/5 times, okay, and so it will be 2 to the 5th plus, and then all of these, they're just 2 to the 1sts, plus 2 to the 1st times 4. Okay, so this is 1/5 times 32 plus 8. So that's 1/5 of 40. And so that is 8. Okay. Which hopefully is the same number that we got when we did this the first time. Let's see. If I flip back real quick here. Then remember that going all the way back here, when we did this way back when, we counted the monochromatic necklaces, and there were 2. We counted the dichromatic necklaces, and there were 6. So in total, there were 8. Okay, so we get the same number here. Okay. Now, to wrap up this video, I want to note, why is it that 5 and 6 worked out so differently? And the answer why 5 and 6 worked out so differently, you probably guessed, is that 5 is prime and 6 is not prime. Okay. And so it's a property of primes that if you do this technique where you take some number of rotations and apply it repeatedly, you'll always visit every node before you get back where you started. Okay. And it's a property of non-primes that there's always a way to get back where you started without visiting all the nodes. And so, for example, in the case of 6, if you go back and look at our diagram from before, what you'll see is, okay, well, r squared gave me this particular thing. And that's because the squared divides the 6. So when you go 2 steps, 2 steps, 2 steps, well, I've now gone 6 steps. So I'm back where I started, and I certainly haven't visited everywhere. Okay. So for any composite number, in order to do this, you're going to have to go back to using the Polya enumeration theorem. Whereas for prime numbers, it's always going to work out so that you can get by with what we did before. All right, so that basically tells you, hey, if I want to do this for necklaces of any length, I know how to do it for necklaces of any length. Okay. I'll put one of those in the homework for you so that you can practice that. But next up, I want to show you some other cases, some other things that we could color, and see how this theorem works out for those.